That teacher must have got there down the hall. That class gets wild waiting for her. Maybe that's what I need to do, is be real late. And so you guys would be out in the hall discussing things, figuring stuff out. We're in lesson 14. Let's get this chapter 10 PowerPoint. It's in lesson 14. Go ahead and grab it and we'll take a look at it. We have some really good information in this one, but it's kind of blah. I think I have like another one. Hang on. Not so boring. I sort of do. So this one is not available on Canvas. It's okay because it's just a couple of pictures that I want you to kind of think about as we get started. If you're looking at a flow chart, a file is usually shown using this cylinder symbol because it's sort of a disk drive is kind of what this symbol is considered. So you'll see this on a flow chart if we have a file, a permanent file that's being involved in our processing. And so far, everything that we've done has been so temporary, right? Like we run a program, we type in our test data, and then it's gone when our program is done running. Well, we know that we have to have things that are more persistent. So to keep data around that we can process again or in another way, we've got to save it in a file. And you guys are used to working with files in our operating systems. Lots of things we could talk about when we talk about files, like path names and how to get to a specific file, different types of files and how they're opened and processed and things like that. But the main thing we need to remember is our operating system is comprised of files. Its main purpose is file management. Files are basically the important thing that we work with day in, day out. We save our Python source code in a file. We tell the Python interpreter to execute the code in that file. We save a PowerPoint in a file. We save an image in a file. We save text in a file. So we can have a lot of different types of files. But no matter what we save, then we've got that data in a persistent format where we can read it again and do additional things with it. So I want you to think about two main different types of files, program files versus data files, and kind of what's the difference. Here's a data file. We've kind of looked at this picture a few times when we're talking about arrays. We have a student file, and in our file, we have several records. Each row in our file is a record. Each record or row in our file then has multiple columns, and each column is considered a field. This is the same terminology that we'd use if we're talking about databases. So it's terminology that is critical for us to kind of get adapted to, that a row is a record. Now, in this record, we have the person's name is one field, and then we have like 4 test scores is our other fields. So as we look at this file, we can see that all of the records in the file contain the same type of information, just about different students. So if I want to process all of the students, I would read all of the rows in the file. I could read those into an array or do whatever I wanted to with them. This picture is really important because it helps you to identify the difference between sequential files and direct access or random access files. So if you remember having an old VCR video, could you go directly to a spot that you wanted? No, you have fast forward, rewind, do all this stuff because it's totally sequential. That tape, you've got to move that tape to the right position to be able to play it. And early storage media use tape. A lot of companies still use tape for backups. So it's something that we can run into. But that's the original foundation for file processing, is this old sequential media. So sometimes file processing enforces limits that we wouldn't need to be aware of if we only had direct access or random access devices. And that's like a DVD. You might not even see a physical DVD much anymore, these old school physical things that we don't have to worry about too much. But with a DVD, I can go directly to a certain spot. So it gives me direct access to that information at a specific location. If I'm looking at a hard drive or a solid state drive, I basically have that same random access, that direct access to a specific location. So some databases, different types of file technology take advantage of this random access or direct access to specific pieces of data. So we can see some old file handling routines that were built for tape type sequential files. And then we might see newer type technology like database access that handles random access. When we're working with an old sequential type file, we want to process each of those records in our file. So we have to do a specific series of things. First, we have to open the file. When we open the file, we're usually identifying the file name that we want to open. You know, maybe its location on our computer. Is it on the C drive? Is it off someplace else? Is it on the network? So we have to open that file. Then we're going to read a record from the file and check to see if we were able to read a record. If not, we'd already processed all the records or the file was empty, we'll close the file and stop. But if we are not at the end of file, we did get a record, we'll process it and then we'll read another one. We'll check to make sure we got a record. If we did, we'll process it. So our control, our flow is just a looping process looking at each record in our file, kind of like we would look at each row in an array as we're processing a list. So those looping type things. Okay, so back to the textbook presentation. They refer to those two types of files as text files, like sequential, versus binary files that are program files, things that maybe have been compiled to run. A text file is something we can read, and we actually in the C# class had trouble last week or the week before on an assignment because there was text embedded in the file that was not readable by humans. It was something that did not result in a readable character. So we can have some text in files that might not necessarily be readable. We'll try to look at that today, later. And then binary files are considered to be things that have been compiled, you know, they're ready to run on the system. They're not really readable by us. They're only readable by a special process on the computer. We saw already we could split up our different types of files by their access method. It's another way we can compare different types of files. Now, if we have a text file, we can just use a plain old text editor to update it. We need to be careful with a text file to not use something like Word. If we update a text file with Word, we could potentially put Word control codes or things like that into our file that our programs wouldn't be able to interpret, could cause trouble. So we want to use Notepad, very simple text editors like that when we're working with text files. These files we can usually display or print without anything special. And pretty much any computer system could read a text file. We don't have to worry about, things like Mac software versus Windows software when we're just working with text. As we saw, each of our files can be broken up into related data or records. Our records contain data items, and each data item in a record is called a field. And business might keep a file for customers. The data might be customer name, address, phone number. So a record of one customer would consist of the three fields, the name, address, and the phone number. Sometimes students get confused and they interject the data into the definition of the file. Let me bring this one back up. So if we were to look at this file, we would say field 1 is probably, student name. Now, when I look at creating the template for this file, I would have student name, maybe score at unit exam 1, unit exam 2, different fields. I would not, however, use any of the data contents. So in no way would I ever say that this field 1, is the Abrams field, right? Because that's just a data content within that row. This is my student name, and this is individual instances of students. So we always want to be really careful to separate our data attributes, the template that describes the data, from the data itself. Kind of like designing a house. If we're designing a house, we want blueprints, but we don't necessarily want the blueprints to specify that the living room is going to be blue or anything like that. The blueprint is a template. It's what we're going to use to build, and that's how we describe the fields that are in each record. Here's our data file again that I used in that other presentation for our students. If we are looking at a comma-separated file, they're pretty common when we're working with text files. A comma-separated file, or CSV, is going to be in this kind of format here down at the bottom, where we have quotes around our strings and commas between each of the different fields. And then at the very end of that record, we have a carriage return. That's our \n control code. That's not something that we would see when we look at the text file, but that control code would be there within that file. These are the first two records out of that file and what they would look like if they were in a comma-separated file or CSV. When I'm looking at direct access files, I can process things independently of the rest. With a sequential file, I can't. So I want you guys to kind of be thinking about like the IRS files, the Internal Revenue Service. So do they have you in their files? Well, probably. And the interesting thing about some of the government files like that, the IRS in many cases still only has sequential files. So they might have, 75 tapes with information, sequential information about all the taxpayers from Missouri or something like that. So they don't have the disk space to be able to take that data and put it into a direct access type format, maybe parts of it. But we have to sometimes live within those limitations, that we have to process files in a sequential manner. So when we're doing that, we're going to process them in the order they were created, and it's just linear. We're just going to do the next one. If we need to, they mentioned this, if we need to print the 50th record, we'd have to read the first 49 with some sort of counter and then print out the 50th. So we wouldn't have any magic way to do that. This is a narrative of the flowchart I showed you earlier. where we're creating or processing a file. We have to open our file, specifying its name. They mentioned that we might have two different names here. We might have an external name, which is the file's name on the disk drive, and then an internal name, like maybe a short name that we assign to that file for us to use in our program. And then we'll also, when we open the file, specify how we're going to read it. Are we just going to read it, or are we going to update it? Or are we going to write new data out to it? So we have to be pretty specific when we open our file. Finally, after we've processed it, we'll close our file. And closing the file saves the file and puts an EOF or end of file marker after the last record. So each record is going to have a carriage return control code at the end of it. And at the very end of our file, there will be an end of file marker. We can't see any of those because, just like our \n, they're non-printable, but that is still in our file. Now, if we don't close the file, let's see, you know what that's like if you've ever fried a flash drive, and so now you're good about safely removing them. If a file is still open on that flash drive, you won't be able to safely remove it. Windows will say, oh, this drive is still in use. And that's one effect of programs not properly closing files. Another effect could be that we can't read that file in another program because it's still open someplace else. So we always have to be really careful to make sure we properly close our files. They have some nice examples here for us. They say we might see a command like this in pseudocode that tells us to open grades for output as new file. So in this case, grades, the thing that's in double quotes, is the name of the file in our operating system, and new file is the internal name we've assigned this file for our program. We're going to be writing to this file, so we say we want to open it for output. And then when we're done using it, we can close the file. So in this example, they go a little bit further and add a loop structure to read the file. Bless you. So here we go. We're going to open our grades, read our grade file into our different variables. And then if we're not at the end of the file, we'll read another one and process it. So we'll just keep looping through all of those records. Take a look at this pseudocode. It should look familiar. It looks just like the two-dimensional array that we created last time, right? We asked for student scores, and we took like 5 scores per student and saved them in a two-dimensional array. Well, in this example, we're going to actually save the data to an output file. Our output file will be named grades, is the file name in the operating system. Our program is going to refer to the file as new file. We're going to prompt for a student's name and test score and enter 0 for both of them when we're done. It's kind of awkward. But we'll input then, we'll read from our user the student and the score. And as long as we were able to get something from our user that wasn't zeros, we'll write that data to our new output file and then prompt them for another one. We'll keep with our loop going until our user enters 0 to say that they're done. Notice with this pseudocode, we prompted the user before we started our loop That's like our priming read. And then within our loop, the first thing we do is take the data we've already got and write it out to our file, and then ask for more data to write out to our file as our loop continues. When we're all done, we'll have created that file, so we'll close it. We'll do an example like that in just a second. But I'd like to kind of look through some more of our presentation before we do any. Whenever we're working with files, we have to have a way to know when the file has reached its end, and that's called the end of file marker or end of file function. The end of file function might be a test condition in your loop. In our example pseudocode here, it has the value true if we've reached the end of the file. So that's why in our flowchart and in our while loop, we're using the negative, saying if not end of file, meaning we actually did get some data. So if our end of file function returns true, we've reached the end of the file. So here is a good example in this pseudocode. We're starting out with our student and score variables. In this example, we're opening the grades file that we had written earlier. We're saying that it's named grades in the operating system, and we're going to call it grade file in our code. So as long as we're not at the end of the file, we're going to read that information and print it out. Now, sometimes that data that's in our file needs to be updated. So if we're working with a database, it's a pretty much an in-place update. I would have, say, your student record displayed on my screen. I would type new data and the code would update that database record. But when we have a sequential text file, it's a little bit harder. It's a little different. Sometimes we might need to delete a record out of our text file, or change one of the records that's already in the text file, or maybe even add a new one. So we have to do some special processing that's a little bit illogical to us. We have to read the file one record at a time and rewrite it to a temporary file or a separate output file. They call this a scratch file. We could see that maybe in our temp folder of Windows. We would see some temporary files like this that are created to update something. Now, when we're doing this, we would be reading the input file and writing the output file, our scratch file. Whenever we're changing things, if we're modifying an existing record, we would just make the change, the update, and write the new modified version out to our output file. If we needed to delete a record, we just plain would skip over it. We wouldn't write it out to our file at all. And if we were adding a new record, we would have to find the spot in our file to add that new record, then write it out to our file. Now, if we end up deciding that this new record needs to be added to the end, we would have to read to the end of the file and then write our new one. So modifying a sequential file is a little bit more complicated than modifying something that is direct access, because we could just read the specific item and modify it. Here's some pseudocode. I'm going to give you a second to look at it. Think about the logic going on here. This is a specific delete process. And in this process, we're just asking the user for the name of the student that they want to delete. Notice that we opened two files, one for input, our grades file, And then for output, we opened a temporary scratch file. We ask for the student's name to be deleted, and we read through our file. Each time we read a new record in our file, we check to see if that's the student we want to delete. If it's not, we go ahead and write it out to the output file. But if it is the student we want to delete, we'll just ignore that record and it won't be written to our output file. So think about this logic. It's something that also we could do in an array if we wanted to update or remove an item from our array. Now, important point though, we created that output file as a temporary file, our scratch file. So our grades file now is obsolete, right? It's not our newest version. This scratch file is the newest version of our grades file. And we want to make sure that it's the one that anybody would read if they want to read the grades file. So in this example, they're just taking the scratch input file and now writing it back out to grades. Remember, in our first process, we can't read and write to a file, a sequential file, at the same time. It's not possible. We can read from it and we can write a new one beside it, but we can't read and write to the same spot because it's not direct access. So we have to have a process that follows our update program to make sure that our temporary file is copied to the location and becomes the new version of our permanent file. They have a note down here, the scratch file still contains the information, but it doesn't matter. The next time a process opens the scratch file, the old contents will be erased and it'll start all over with a new version of it. Now take a look at this pseudocode. You can see it's an even more involved process. So what do we have going on here? In this one, we know what student we want to modify, but we just want to change their score, their test score. So again, we're opening on our grades file for input and opening a scratch file for output. We ask for the student name and we ask for the new score. And then we start reading through our file. As we read each row, we'll check to see if this is the student to update. If it is, we'll write their new score out to the file. Otherwise, we'll just write the existing score and data out to the new file. So this process will let us update the score for one student. When we're done, we'll close both files. Take a look at this pseudocode. Remember, while you're thinking about it, be thinking about those IRS data files all on that sequential media. Sometimes people ask questions like, why don't they check, people's, or they think that they check people's, employment record against their tax record. Nope, they only use that W-2 or whatever it is that's printed out at the end of the year because it's a huge process. They have all these sequential files. So this would be a reason why it's taken many, many, many years to merge student loan data with tax record data. Some of the government files are so huge and are still on such sequential media that it makes it really long and involved to match them up with something else. This one is an example. We want to insert a record here. So again, we've got to read our grades file as input and create a temporary output file. We're going to ask for the name and score of the brand new student we want to insert in our file. Now our while loop notice is a little bit more complicated because while we can read records from our file and we have not inserted a new record, we want to read from our file and check to see if the new name we just read is less than the new student we're going to insert. If it is, we'll go ahead and write out that new record and modify our inserted flag to say, yep, we've inserted one. And then we'll continue writing out the data that we've read. So if we do get to a point where we're ready to insert, we'll insert the new student, then write out the record that we had read that, that let us know we were at the right spot to insert. Now, when our while loop gets done, because we actually insert that student into our file, we'll just write out what we've read every single time because we know we don't need to do that comparison anymore. At the end, we're just going through our file and reading and writing everything that's remaining out there to our new file. So this insert process is a little bit involved. Sometimes we have all the data that we need to write to a file already in an array, or we can take the data that we've read from a file and put it into an array. This allows us to process all of that file data using memory, but it only works if our file is small enough to fit. If you can think about the giant IRS files again, they are not small enough unless they're taking a very small sampling, like, maybe people in a certain zip code might be small enough. Now, this also works good if we have a lot of changes to make to our file. Our internal memory, remember, works the fastest, and it can be a lot more efficient than writing to that scratch output file. In this case, we would open the file for input, read the records into arrays. Notice they say we would need many parallel arrays. We would close our file then, make all of the changes we want to the data that's in our arrays. Then we could reopen that same file for output, which makes that file blank, and write out all of the contents of our arrays to the given file and then close it. So lots of ways that we can handle it. This example shows us that sort of thing where we're going to say we have space for 100 students with 2 test scores each. And we're going to read all of this information from our data file and add the data into our arrays. Then we'll open our file for output and process our arrays, writing the data out. We would have had some sort of update event occur in between that input and output processing so that we've updated the data in the arrays. Now, this is the last little thing that they want you to think about. And again, think about if you were working and you have tax files and student loan files in some other sort of file that you needed to all merge together to find information about, Joe Brown. Joe's not been paying for his student loans, and they want to know, has he been paying his taxes? Has he been filing income taxes? Does he have bank accounts? We got to merge all this data, huge quantities of data from many different locations. So if we want to merge, say, IRS tax data with student loan data, we would have to open both of those huge files for input, and then we would open another file for output to hold all of the merged data. We would read records first starting out from file 1 and file 2, And then we would have to check something like maybe our last name sort order, social security number, something like that. If file 1 is less than the number that we find in file 2, then we would write out the smaller of the two records to our output file. So we kind of decide which one goes first in our output. Now, after we've got file 1 completely processed and file 2 completely processed, and we've merged the data within those two files into file 3, we can close all 3 files. They give us some kind of general pseudocode for that. It's really, really general, but it's a good thing for us to be thinking about because this sort of merge process is something that we don't encounter a lot while we're in school, but we encounter it a lot in the real world. They have an example for us here, the big merger. So we have a company that wants to merge 2 payroll files. And I have some former students that work for Jack Henry, the banking software company here in town, and their responsibility is to take, like a new bank that buys Jack Henry software has to go through a conversion process. They have to take all of their files in whatever format they're in right now, and they have to somehow convert them to be in the file format that Jack Henry uses, that Jack Henry wants. So these former students are that department. What they do is take the data from the banks that have just bought software and they write code to actually do the conversion. So they do this kind of thing quite often, and they're doing quite well financially. So this is something that can be really important to companies in many different ways. So for this example, I kind of think of it that way, is we probably have some sort of acquisition going on where maybe company 1 has bought company 2, and so now we've got to put their 2 payroll files together into a single file because we're becoming a new company. So each of the records has a certain form. We have the employee number in an integer format, the employee name, and then their rate of pay. The records are in order by employee number, and the last record in each file is all zeros. So we're going to merge the 2 files into a new file called payroll. So they have all the variables here set up for us on this first slide. And then if we keep looking, we'll see that we open our 2 payroll files as input and the new payroll file as output. We read data from our first file and our second file. And as long as we have an employee number to look at there, we check to see which file has the lower employee number. And that's the one that we write out first. And then we read another record from that file. We keep doing that process in our while loop until one of our files kind of reaches the end. When we've hit that point, we have to check to see which file it is that has hit the end of file, because we need to process the other file until we get to its end too. And then, whoops, we'll finally be done. We'll write our end of file marker of all zeros, our internal one, out to our new file, and then close all 3. So we do have a lot of logic going on there. Here's our big merger input. Payroll 1 has Art, Ben, and Kyle, and payroll 2 has Dan and Eva. And if we look at this, you could think of doing it in Excel and think of how easy it would be. They would just copy and paste these 2 pieces of information and then sort by the employee ID. Easy peasy. Well, we can't do that with the 2 billion records that are in the IRS files. We have to process them sequentially. So we have to do it programmatically. But after our merge, we should end up with the same kind of output as we would if we were able to do it real quickly and easily in Excel. So sometimes we have to do things programmatically that would be real easy if we were just working with a little small amount of data. But since we're working with massive quantities, we have to do it a little bit differently. Along those same lines, when we're working with a lot of data, we might need to do what's called a control break. And a control break is where we calculate like a subtotal. Let's find an example here before we look at this because it's an important concept. So let's say I want to look at a group report. I'm going to do images here and see if I can find something. This one is good. Here's Christina Berglund here. She's got some sort of snack shop. And she has things grouped by the amount of discount that they're offering. So their Boston crab meat does not offer a discount. So we see that that's the only detail item displayed for this 0% discount control break. But then after that, we have items that qualify for a 10% discount. So we list each of those, and then we will have some sort of subtotal down here at the bottom for a total of things that are discounted 10%. This report then could keep going and going, giving all of the different discount amounts. In this example, we're using the discount percentage is our break field. That's the one that if it changes, we want to calculate a subtotal or print out our existing subtotal, maybe reinitialize some of our variables used to keep the subtotal, and then continue on with the next set of stuff. So whenever we calculate a subtotal like that, we're using a control variable. In our example, it was that discount percent. So here they have an example where a program accepts a monthly sales amount from the user. When the month changes from January to February, we want to print out January's sales subtotals and then start adding up February's sales. We would do the same thing then when our month changes to March. So control breaks are a very common processing thing that we have to be aware of also. Whew. They have a lot of good information in that presentation. It's sort of stuff for you to be thinking about, having in the back of your mind as you move forward, looking at more advanced classes and doing more advanced things. So let's do a little bit of practice. There's a couple of places we can go. The first one is Runestone Academy. I'm going to copy this link and I'll paste it to our chat so you can grab it. It's also in our Canvas stuff for this week. So you can find it again. So if you'll go to that link, this is a website that we haven't used before. And it's not as pretty and interactive as Code Academy, but it's actually where our Python tutor site comes from, where we're able to visualize code. So this site has some great things, even though it's not as pretty as Code Academy. But it's a site that is kind of called open source, meaning that, you know, it's all free and they're trying to create, just like some of the other sites, available education materials, except that they don't ever plan on charging people like Code Academy and W3 Schools do. Now, the way this site works is this link that I gave you takes you straight in to this open source textbook that they have. It's called How to Think Like a Computer Scientist. But they have some other textbooks on this site too. You can find them if you click up here at this link Think CSPY, because that's their abbreviation for Think Like a Computer Scientist. So I'm going to click on that. What are you doing? There, it's finally thinking about something. And I want to look at this R library link. And these are all of the different textbook titles that they have here on this Runestone Academy free library. Every time I think of the URL, it always makes me stop for a second. What was it, that old RuneScape game? I don't know if any of you guys ever played it. Used to have students that were addicted to it. So it's just, it makes you think about some old games. We'll take a look at the information on file handling as soon as our break is done, unless you guys don't want to take a break. It's up to you. We're at the end of the semester. Let's just go ahead. We've been doing it for this long. We'll start back up at 9:20. I'm sorry, I can't hear you. Okay. Okay, hope everything's okay. Oh, let's get back to it. You're still here. Looking at Runestone, these are the textbooks that they have. So they have a lot of beginning level things, computer science concepts. So it might be something that you want to look at, through the summer, depending on what you're going to do. They have some that might help with the data structures class, the database class, and then the intro stuff. They have some Java, Python, the How to Think Like a Computer Scientist Interactive Edition is the one we're looking at. So we're not really looking at the actual Python course. They have a lot of great stuff. So I'm going to go back to this How to Think Like a Computer Scientist textbook. And we want to scroll down. And let's scroll down to chapter 11, where they talk about files. So if you click on 11.1, working with data files, you'll get the ad that supports them being free. So I guess it's okay. Now, the first blurb of information, if you read through the information, they'll tell you about opening files and the exact Python syntax to do that. So we could make sure that we're using the right syntax to open and close files. Now I'm going to come up here to the top and click on the next link. They have a next button, but I'm not necessarily seeing it well without being logged on. So you can certainly set up an account if you want to, but I don't want to, make you do that. Oh, there it is. It was hidden by their ad stuff. So once I close that down at the bottom, I can see the next and prior buttons. So in this page, they're talking a lot about how to find a file within your file system, looking at your hard drive. And that's one that I want to look at real quick. A lot of people have been using computers like almost their whole lives, but they don't know much about file systems. So here, looking at File Explorer, I'm looking at the top, the common folders on my drive where I save things. In the middle, I'm looking at my actual hard drives on this machine. I have the C drive, and then I have an external drive attached. And then at the bottom, I see network drives that are attached to my computer. If I drill down and I look at the C drive, oh, that's important, our drive letter too, the C colon, E colon. Every drive that we attach to our system in Windows is assigned a drive letter like that. So if I'm looking at a full, absolute path and file name, it may start with the drive letter like C colon /. So in this system, if I'm looking at the root of the C drive, which is the C colon / folder, I would see all of these folders that are on the computer. If I click on one of them to open it, I could, let's go into the program files folder. Now this program files folder has a lot of different folders in it. I could keep zooming down into each one of those to see the contents of that folder. But I want to look at the DOS, the good old DOS command prompt when I'm looking at this folder. So up here in my address bar, I'm going to click. And first thing to notice is when you select in the address bar, the display changes and it shows you the actual path name that you're in. So right now my path name is C colon / program files. I'd like to go to a command prompt there. So right here in my address, I'm going to type CMD and press enter. And that's going to open a command prompt window there in my program files folder. So that's my current folder, is C colon / program files. Now looking at a command prompt, I can do a dir command to list the contents of this directory, because directory means exactly the same thing as folder. It's just the original term. So if I do a dir command, that'll show me all of the files and folders within this folder. What I'm interested in are these two here at the top. Whenever I do a dir or a directory command, I always see these two special files at the top, and the dot stands for the current folder. So my current folder is C:\program files. So if I were to do a command and use the dot as a file name, it would replace that dot with this path of my current folder. Now, that's what the dot means. So that's used for relative addressing, which is what I want to use in my program code. I always want to say, oh, the path to that folder relative to the folder you're in right now is this, like starting here and going there. Now, how I can move around using relative path names is by using the dot parameter. The dot parameter means the parent folder. The parent folder of my program files folder is the root of the C drive itself. It doesn't have a separate parent. But if I were to go down into this Android folder, its parent would be program files. So I can actually use that dot and dot. Let's try it. If I do a directory of the folder that's indicated by the single period, that will be my current folder. I should see the same directory listing. I saw it entering the dir command without the dot. So I'll check. Yep, my program files folder. Now, if I do a dir command using the two dots saying, go up to the parent folder of where I am and do a directory command, I'm going to see a directory listing of the root of the C drive. So whenever you're in web design and you're using, you see in your HTML code, it has this like dot / or dot /, that's saying starting at the current folder, follow this path. So path naming and pathing can be pretty interesting when we're working with Windows, but they have some good examples here. Looking at this graphic, we have a My Files folder, and it has two folders, Other Files and All Projects. The Other Files folder has another folder called Extra Data, which finally contains a text file. The All Projects folder has two folders, My Data and My Project. The My Data folder contains two text files. The My Project folder contains a Python program and a text file. So if we are sitting in our My Project folder and we want to specify the file name of the data1.txt file, we could just say data1.txt because we're already in that folder, so the relative path name would just be the file name. But if our current folder is the My Project folder and we want to specify the path name to the data2 or data3 text files, we have to get a little bit more creative. We have to say first, go to the parent. That's why we see the dot here. Once you're at My Parent, you should be able to find a folder called My Data. And once you find that folder, you should be able to find the data2 text file or the data3 text file. So notice how the two dots indicated how to follow the path to get to this file from the folder that I was currently in. Now, if I'm in this My Project folder and I want to specify a path to get to the data4 text file that's way up here, I have to use the parent specification twice because I have to say first, go to the parent of the My Project folder. Ah, that's all projects. Now, go to the parent of that folder. Oh, that's the My Files folder. From there, you should be able to find the Other Files extra data folders to find the data4.txt file. Now, these path names here are all relative to my current location being the My Project folder. If I wanted to specify an absolute path to that file, I could, and I would start with either the drive letter or a slash to indicate the root directory of the drive. But if I do that, then I'm giving an absolute path name. And looking at this very bottom open statement, notice how this file is in this users folder. So I wouldn't be able to run that code, right? Because it's specifying B. Miller's folder is where to find this text file. I don't have access to B. Miller's files, so I never want to use an absolute path like that in my program code. I always want to use relative path names, whether I'm doing web development or programming, so that my path is relative to the project folder. Because my project folder is always going to exist no matter what computer I put this code on. So as long as I specify the path based on that location, the easiest way is to just copy all of the data files we need into our project folder, like they did here for the My Project folder. And then we can just specify the file name because we're in the same folder. We'll do some activities on Replit, and Replit will kind of handle it that way, like everything in our Replit is in the same folder. So it makes it a little easier for us than if we were doing it outside of Replit. Now, here's an example reading a file. We have this file called CC data, and we have the year and the global average temperature and the global emissions of CO2 registered for that year. So if we want to read this data file, first we need to open it. They give us an example down here of code to open this file. When we open it, within our open function, we're going to pass the parameters of the file name, ccdata.txt, in our open mode. We just want to read it. The short name assigned to that file for our program will be file ref. So when we want to close the file, we use that short name to specify run a close on it. Now, let me get this add out of the way and go next. If we wanted to read all of the lines in the file, we would add a for loop. We could use a for each loop like this. This code is already here for us. It opens the file, and then for each line in our file, we use the split command to split all those pieces of data into the separate fields, the separate values, and then we print out information from each of those fields. Let's see if we can run this. There it is. We can run it right here in the Runestone Academy, and here's our output. We could try changing up our output a little bit. So let's change it a little bit. Instead of saying the average temp was, let's just say something shorter like AVG temp. And then I'm going to run this again. And you can see that it'll run the code exactly as we have it here in the Code Lens window. So this would be great code for you to refer to if you were going to read a file, like in the assignment. Now I'm going to keep going, and in the next example, they're going to show us some other ways that we could read things. We could read individual lines in our file. If we do the read line command, we just read the file one line at a time. But if we do the read lines command, that reads all of the lines from the file at once to put them into an array for us to process. So Python gives us both of those statements, both of those functions. We can read individual line in a for loop, or we can read all of the lines from a file all at once. They also give us some examples on how to write data out to our file. We would use the write function, and it's exactly the same as the Python print function. It's just that the write function specifies what file to write to. So whenever we're using the print function, we're always printing to the console. But if we want to write to an output file, we specify that short file name with our write function, and then the rest of everything would be the same as if we were printing something. Now, here's an example that we can run and interact with. Again, we're opening our file, but this time we're going to read the first line, and we're using a while loop to process it. So we're saying while you got a line, which is exactly the same as saying while we're not at end of file. While you got a line, split the record up into its individual fields, print out the individual fields, then read another line from the file. Notice this is just a little different than using that for each loop, where the for each loop takes care of when the file gets to the end for us. So we can run this, and we can see that when we're done, we close the file. They have a lot of information here in the reading. I just wanted to show you how they're giving you exact examples of everything that you need to do. So let's look at the Replit assignment and see if you feel like you can accomplish it based on this information. Now, besides this information in this Think Like a Computer Scientist stuff, W3 Schools does have some information about working with files. Let me find it. They have a whole kind of little baby section here for Python file handling, and the W3 Schools presents it in the same kind of way that we have our open statement, where we have to specify our file name, and then they show us how to read files and how to write or create files. So two different sources of information. So let's look at our assignment. In lesson 14, I want you to look at this Replit, file and image processing. I'll try to open it in Firefox, but I don't know if I'll be able to. Nope. My account is just something I can't remember in Firefox. So this Replit has two sections. The first one is file processing. That's the one I want you to work on today. Let's take a look at it. Next time, we'll look at the glitch and image. But in the file processing exercise, for our instructions, they're pretty basic. They say that you want to use the Runestone Academy to find instructions. And this Replit includes a file, qbdata.txt. If I look over here in my files, I see, oh, there's qbdata.txt. Let's take a look at it. This data shows us some information about quarterbacks, but what in the world? Well, this info file tells us what each of the fields are in our QB data file. So first we have the quarterback's name, and then their position on the team, which is always quarterback because we're looking at quarterback data, the team they're on, and then 7 fields of statistical information. So we don't have to worry too much about the details about what each of those items are, you know, like their percentages and things like that, because your Python program is going to read this text file and it's going to create a new file for output. So we want to read the text file, and create an output file named qbnames.txt that just contains the quarterback's names. So in your program, you're going to need to read the QB data file and create the QB names text file. So we have quite a bit of time for you to do that, looking at your resources. See if you can create that program on your own. Let me know if you need a little help, but I think you can do it with our sources. So I'm going to shut off our recording. I think we've got everything there, and that'll be it for us for today. So when you're finished with your lab, you can get out of here. But like I said, if you have any questions, let me know. Please try to finish this before you go.